of the deepest concepts in all of physics is the idea of a conservation law. We say that a quantity is conserved in physics when it always has the same numerical value before and after some process. There's several important physical quantities that we'll learn about that are conserved in Physics 6 and in Physics 7. And there's some others in more advanced applications of physics. But in Physics 6 and Physics 7, we'll see that energy is conserved, momentum, which we'll learn about in Unit 7, angular momentum, and charge, which we discuss in Physics 7. Anytime you have a system that has no non-conservative forces, then that results in mechanical energy being conserved. And I'll show you why. In the last video, we had this relationship that the work done by non-conservative forces equals the change in potential energy plus the change in kinetic energy. So if there is no non-conservative force involved, the left-hand side of this equation becomes 0. And if we identify a quantity called total mechanical energy as the sum of potential plus kinetic energy, then that mechanical energy always has the same amount. So let's define E, the total mechanical energy, as potential energy plus kinetic energy. So that means delta E is delta PE plus delta KE. So in the case of no work done by non-conservative forces, we have this relationship that delta E is 0 and mechanical energy is conserved. So, as we broaden our discussion of energy, we'll expand this concept of conservation of energy to include all types of systems, even when there are non-conservative forces, and we see that it still holds. So it turns out that this is saying something very deep about nature, which is that you can't create or destroy energy in nature. It just turns into different forms, but the total amount is always the same. That's a really deep physical principle about how the world works. Not only is that interesting to think about, but it turns out that it's super practical for solving problems. And I want to start doing some sample problems with you now. We can use this conservation of mechanical energy to solve problems that would be difficult or even impossible to solve using Newton's laws or kinematics, some of the other tools we've learned before. So this is now going to be an important tool in our toolkit. Let's take a look at some of the examples from the textbook. Example 5.5. We're returning to the idea of a diver jumping off a diving board into a swimming pool. So here's the pool. Here's our diving board. There's the diver. And let's say that that initial height is 10 meters. And we'd like to answer a pair of questions. First question is, what is the diver's speed when they reach the halfway point down? Okay, we can use our law of conservation of mechanical energy to solve this problem because there are no conservative forces involved, ignoring air resistance or friction or anything. So here's how we do problems like this. We can start out with this statement that mechanical energy is conserved, and let's write it out completely. This means potential energy final minus potential energy initial, and kinetic energy final minus kinetic energy initial all add up to equal 0. And if we move things around a little bit, we have PE initial plus KE initial equals PE final plus KE final. And that's going to be our most useful form of this equation. That's just another way of writing this statement that mechanical energy stays the same the whole time. And now we replace each of these quantities with the formulas we've learned. So we just learned the formula for gravitational potential energy. It's mgy, and I'll write y initial for the initial height of the diver. We've learned a formula for kinetic energy. It's 1/2 mv squared. There's v initial. And similarly for the final potential energy, mgy final, and 1/2 mv final squared for the final kinetic energy. And now we think about the values we have for these quantities. Some of them are 0. The diver is starting out stationary, so v initial is 0. So we can just cross that term out. And the diver ends up at water level, and we might as well call that 0 height. So let's say that y final is 0. Oh, I'm sorry, for part A we're not at water level yet. Part A we're halfway down. That'll be for part B. Sorry, part A, we've got y final is 5 meters. So I won't cross that term out. Okay, so we're interested in finding v final when the diver reaches this halfway point of 5 meters. So we do a little bit of algebra. All those m's cancel out, and we find that v final is 2g y initial minus y final square root. Try that algebra out at home. And when you plug in these values, y initial was 10 meters, y final is 5 meters, you find that the diver's speed halfway down is 9.9 meters per second. Now, if you think back to the first few weeks of class, this is a problem that we could have solved using kinematics. So if you're curious, you might go back and analyze this using kinematics techniques and confirm that you get the same answer. So right now it looks like we have two different methods for solving the same kind of problem. You could either use kinematics or you could use energy. What we're going to see as we expand our repertoire of energy problems is that we'll eventually get some problems that are so tricky that kinematics doesn't work anymore and Newton's laws don't work anymore. I mean, those laws are still true, but mathematically they're too hard to deal with, and conservation of energy becomes more useful. Okay, part B. Now let's ask how fast is the diver moving when they hit the water, and we can use our same equation, just now with y final equals 0. So when you plug in y final equals 0, you find that the final speed when hitting the water is 14 meters per second. I'll do another example in the next video.